All right, so I'm going to take your lab results and help you figure out an equation, right? Sound good? That's all. And a lot of you have already done this. Cool? And I'm just going to remind you of the logic behind what you did, okay? So I promise you, you draw energy flow diagrams, you'll get it. If you don't draw energy flow diagrams, hi Maria, you'll have trouble, okay? And I've seen this already in honors. Like most students are actually saying, all right, these energy flow diagrams are really helping us, and they're all doing it, and their worksheets are easy. But the few students who just tried the equations, they're just trying to use the equations only, are really struggling. And they're starting to do the flow diagrams, and then it's easy. Okay? So, let me remind you of what your lab was. You stretched this rubber band, and it launched a car, right? So the first moment in time was what? Help. What is 0? Huh? So you're saying the velocity was 0. What can you tell me about the rubber band? Okay, so all the energy is stored where? Try it again, everybody. You guys cool with that? Careful. Thank you. So we're not worried about EG. We're not worried about EK in the beginning. Is it moving in the beginning? I'll add V equals 0. But you're correct. There's energy stored in the rubber band. So our system is what? Car and rubber band. Good. And in the end, what's true about the car? Is it moving? What's true about its velocity? We would say it's what? It's constant, and it's the maximum velocity. And technically, this would be the moment immediately after the car has left the rubber band. So I'll draw my rubber band here, but the rubber band's slack. It's not stretched. And the car is not touching it anymore. You guys cool? And what are we ignoring in this particular problem? Between the two moments in time, is there any force on our system? Okay, so there's no work done on our system. What else? Okay, so we're ignoring dissipating energy. So we're ignoring all dissipating energy. If this assumption is true, then whatever energy we have at this moment in time in the beginning has to equal what? So this number, whatever energy we got in the beginning, there's no EK, no EG. Now in the end, where does the energy go? Okay. Any elastic left? Okay, good. So I can cross out EG, any elastic, and our equation simply becomes what? Okay, good. So E elastic equals EK. The reason students have trouble is they memorize the equations, but they don't understand where they came from. Notice if we use an energy flow diagram, we can see where everything came from. Are you guys good? And we have ways of finding E elastic. How did you find E elastic in this lab? How did you find the energy stored in the rubber band, please? Okay, so try to speak louder, please. F delta X. And you had to do what also? Why is this a triangle? What can you tell me about when you stretch a rubber band? Good. So as you stretch a rubber band, it requires more force. We're assuming that it's a linear relationship. Thus, the height of this triangle is F. The base is delta X. And we got to do 1/2 F delta X to find the energy stored in the rubber band. And we're assuming that becomes energy in the motion of the car eventually, right? And not only that, we're assuming all the energy from the rubber band goes to the car's motion. You guys good? And you measured the speed. So you actually measured force, you measured delta x, and you measured the speed of the car, so you were able to graph EK versus speed. You guys, everything good? So if I pull up, this is a group's data, it looked like this, right? They spelled kinetic wrong, so I'm going to fix that. Kinetic, and this is kinetic energy, right? So I'm going to write it out like that. Everything else looks good. And this is velocity, v is speed, really. All right? And I just showed many of you how to do this. You already know the equation is what for kinetic energy? So you already know that kinetic energy equals what? 1/2 mv squared. All right, so you can see this is a power 2, right? So you can check this with Logger Pro. I just go Analyze, Model. It's a pretty cool thing with Logger Pro. I choose Power. I make B2 for second power. And what was the mass of your cars again? What was half of that? Okay, so let's see how close we were. 0.125. And as soon as I put half the mass of the car in here, it's like magically perfect. It fits our data beautifully. And if all went well, this is how it would have gone. Cool bananas? Now, if I move, I'm going to move this over here, okay? Because I can just prove it to you. Looking at this slope, actually it's not a slope, my bad. It's a coefficient for that curve. So since it's not a line, it's not a slope, right? But this coefficient that you put in this equation here is 0.125. And obviously that's kilograms because it's half the mass of our car. And I'll just copy down the v squared equals EK. And looks really good. Are you guys cool? So we verified our equation. Kinetic energy is what? How do we calculate it? What do you do? I'll try it again. How do you calculate kinetic energy, everyone? If you're going twice as fast, if your speed doubles, how much more energy is in your motion? Try it again. If you go 30 miles per hour instead of 15, how much more energy is stored in your motion? You can use just looking at this and this. If you square velocity, and that is related directly to kinetic energy, what that means is if you double your speed, your kinetic energy goes up by, you're saying it now like one person, everybody? Yeah. It's kind of crazy. If you're going 45 miles per hour instead of 15, how much would your energy go up by then? Yeah. Most people don't realize this, and they drive like silly fools, right? But if you slow down just a little bit, it actually makes a big difference in the amount of energy in your motion, and actually dramatically increases your odds of surviving an accident. You cut your speed in half. You're not doubling your odds of surviving an accident. Your odds are going up by what? Yeah, just by cutting your speed in half. You cut your speed in a third. Instead of driving 90 miles per hour on the freeway, 80 miles per hour on the freeway, cut that in a fourth. That's 20 miles per hour, right? How much safer is 20 miles per hour? 4 times slower, 16 times less energy. It's mind-blowing when you think about it. Make sense? Even small changes in speed will make a big difference. Anyway, so that's your lab. That's it. Thanks for watching.